So, example we have here, two examples of graphs. Please look here. We have two examples of graphs. Before this one ruins. Okay, someone turn off. I have two examples of graphs. What you can tell me about the first and the second graph? Are they the same or different?
They are different.
Same.
She says different. Who said same? Same or different?
Same.
Same. How do you know they are same or different? How many vertices we have?
4.
A, B, C, D, correct? And this is the 4 vertices we have. How many edges I have?
4.
4. What are the edges? A, B connected. This is also A and B connected. This is A and C connected. This is also A and C. B, C, C, D are exactly the same.
Ah.
Right? So we don't look at how we draw it, right? You might draw the graph different way than I draw, right? Because we are not limited like a binary tree, correct? Because graph I can start from anywhere I want. I can put A down, A up, A left, A right, up to me, right? As long as they have the same set of vertices, same set of edges, then they are the same graph exactly. Okay or not?
Okay.
Next. Directed and directed. This is graph is what? What's mean directed?
It has directions.
Yes, the edge has direction, correct?
Yes.
Are they the same or different? Different. What's the difference between them?
Yeah, A to C.
So they are the same, same set of
Directions.
vertices, right?
Directions are different.
But the edges are different, correct? So I look to here. A is going to C, correct? In this graph, is A going to C?
No, it's still going
Is C
to.
going to A? That's it. They are not the same graph. And also one more. What is it? B and D. B and D.
B and D,
B
D
going
and B.
going to B. All right. So they are not the same graph. They are different graphs, right?
24.
Path. What is a
Oh,
path
basically
in
it shuts
graph?
down.
What is a path?
Your network.
Okay. So let's say you are here currently. You want to go on a walk. Okay. So you walk from A to B, from B to C. That is a path, right? Okay. And does a path? Is it possible for a path to be containing a cycle? What does a cycle mean? Go back to the same location. Yeah. Let's say you want to jog in the morning, running in the morning. So you walk around the football field, right? Multiple times. So this is called you are doing cycles. How many cycles you have done?
Did you talk
Right.
about the file?
So
Did you talk about the file?
here I do the same path with what? No vertex is repeated, mean a path without a cycle. Correct? Right? So here I'm going A, B, C, D, A, B, C, D, or D, D, C, A. What is it? D, C, A, right? Okay, and so on. Next, we have a cycle. So, cycle is very important because we have few algorithms later on. It depends whether we have cycle or not, right? So, cycle is a simple path between distinct edges, except that the first vertex is equal to the last vertex. So, meaning that if we start from a position, let's say A4, you went around, you came back to A4, what does it mean? You have done a cycle. Okay, this is how we discover a cycle, right? The first location equal to the last location, right? So here I'm going A, B, C. Not yet I have cycle. If I go back to A again, I have cycle. All right? Okay? And so on. So this one first equal to last, first equal to last, first equal to last. So this is how we detect cycle, right? Okay? If any vertex is repeated, right away you have done a cycle. The cycle also occurs if A go to B. If you go to B, then you go back to A, also a cycle. All right?
What if path is different?
What do you mean path?
Two connections. I mean, you are going like this, and again from different path, but same final.
You mean you go like this, then you come back like this?
Yeah.
So once you come back like this, it means you have a cycle between C and D. All right? Okay? It's not, I start from A, going to C. Do I have a cycle yet? No. I go to D. Do I have a cycle yet? If I go back from D to C, do I have a cycle? Yes, C is a repeated vertex. Right away, I have a cycle. Any vertex from your path is repeated, you have a cycle. All right? This may be more clear. All right. Loop is what? When the vertex is connected to itself. But we hardly ever use it. Okay? Only few applications using loop. Okay? But we hardly ever use this application. connected and disconnected graph, maybe this is important. So connected graph, there is a path between two vertices, right? There is a path between two vertices. Disconnected graph, a graph G, let's say this is a graph G, right? Is said to be disconnected if there exist two vertices in G, so there are two vertices in this graph, okay? In G, such that no path in G has those nodes as endpoints. Meaning that I come to this graph, select two vertices, let's say B and D, right? If this B and D, they cannot be the beginning and the end of a path, what does it mean? Disconnected. Okay? So meaning that if I start from A here, can I reach D? No, this graph is connected, right? Because, okay, it's disconnected, right? There's no link between them. Similarly here, is disconnected or disconnected graph? Disconnected. All right? So, graph and tree, which one? Tree, okay. Now, what is the difference between graph and tree? What is the difference between graph and tree? I want to reach my pen, but I'm scared.
There is no parents in the child's diagrams.
Okay. This is graph or tree?
Graph.
Very good. Can be both, right? Okay. Graph or tree?
Can be both.
Graph or tree?
Graph.
Ah, why graph? I said
Can be
tree
both.
or I said binary tree?
Can be both.
Can be both. I didn't say binary. Binary, two children, right? Okay. Graph or tree?
Graph.
Why now you changed?
Because it's graph.
Do you remember what's the property of a tree?
Unique path.
Unique path between the root and every other node. Do I have unique path to 30?
No, you have two puzzles.
20 to 30, one path. 20, 40, 30, another path. What I'm having now,
Circle. Cycle.
circle. And I do this, it is circle, okay? But it is a cycle, all right? So here I'm going through a cycle, right? So now tell me, what's the difference between graph and tree?
A tree has unique paths. Graph has a cycle.
Meaning that a tree should not contain a cycle, a graph is allowed to contain a cycle.
Yes.
Correct? That's the main difference between them. Right? So coming here, seeing that a tree is, okay, tree under the graph with no cycles, right? Is under the graph with no cycles, and a node can be chosen as the root. Okay? So here we choose node, one node chosen to be the root, which is A, B, and Q, whatever you choose, it should be. Okay? So, tree is a graph. This one, tree 1, is it a tree, correct? Can we call this a graph as well? Yes. So every tree is a graph, correct? Yes. But not every graph is a tree. Right? Okay. This one, graph and tree, right? Spanning tree. Okay, what is a spanning tree? Let's say I have this graph. So we know that tree doesn't contain cycles, right? So I have this graph here, right? A, B, C, right? This graph contains a cycle. Is this a tree? No. So what is a spanning tree? Okay, it is a separate graph that contains all vertices. It is a separate graph that contains all the vertices. I should not leave any vertex, right? And what? And no cycles. And should not contain a cycle. So meaning that I come to this graph, I have what? 4 vertices, correct? What I do, I take all the 44 vertices, I put them here, correct? Now I start adding edges. Keep adding. Does this will form a cycle? No, except. Once I add edge that will construct a cycle, I reject it. All right? This one, no worries. We will have entire lecture. I put lecture aside, on the side. We have examples and 2 algorithms to explain how to conduct it. This is just introduction. All right? So, what is a tree? Is the indices of a graph that contains all the vertices, the spanning tree, without what? Without a cycle. Okay? So here looking at this one, okay, this is the graph. I can generate more than one spanning tree. One different, so meaning that spanning tree is not unique. I can have more than one spanning tree, correct? Complete graph is what? But mean that if I am at a point, I can go to all other points, right? If I am at vertex, I can go to all other vertices. Or if I'm at location, sorry, I can go to all other locations. So it matters if my graph is directed or undirected, correct? Right or not? So if it is undirected here, meaning that, okay, A can go to B and B can go to A with one edge, correct? I don't have to draw two edges. If I want to do complete undirected, directed, that means I need to put two edges, A to B and B go to A as well. But for now, complete graph means a graph with all edges present. All possible edges are there, okay? Then each vertex is connected to all other vertices. So is this graph complete?
Yes.
So A is connected to all other vertices. B is connected to all other vertices, directly connected, right? C the same, and so on. Okay? This is called complete graph. I have two other terminologies, which is also very important. Remember them. Today we need them. The first one is dense graph. What's the meaning of dense graph? Dense graph means relatively few of the possible edges are missing. So meaning that if I come to this graph and I remove the edge between A and B, right? I remove this edge. What happened to the graph? It is not complete anymore, correct? What we can call it?
Dense graph.
Dense graph. What does this mean? Just like when you go to a forest, right? When you go to a forest, it's a dense forest. It has so many trees, right? Okay? It's not completely full of trees. We can walk through them, right? That's what means dense. Meaning the majority of the connections are there. How about sparse graph? What is sparse graph? The opposite of dense. Only few edges are there. Okay? All right? So, sparse graph, relatively few of the possible edges are present. Okay? You know now the difference between sparse and complete? Okay? Sparse, few connections. Dense, a lot of connections. Complete, all connections. All right? So, weighted graph and networks. So I think we can go a little bit faster. We also studied networks as well. So weighted graphs, weight are assigned to each edge. So look here, if I go from A to B, what is the cost? Let's say A is your home, B is your neighbor, C is also your neighbors, and you want to connect them with a cable, right? A networking cable, right? So to connect a cable from A to B, I need, let's say, one meter cable, right? Okay, or 1 kilometer. Will not be a neighbor. Okay, 1 meter, too close, also it's like brother. Right? So I connect one, right? This is the connection cost me 2, this is the connection cost me 4, and so on. Right? This is the weighted network. So network is directed weighted graph. Some theories allow networks to be undirected, meaning the cable can go back and forth. All right? The connection. How to represent the graph? So looking at here, okay, look at here. How do you represent this graph? Can I do nodes and pointers? What do you think?
Pointer.
Somebody say. Which one do you think better? Matrix or two-dimensional matrix? Did you study this one before? Adjacent matrix.
Yeah.
Some say yes, some say no. Who said yes? Where did you study it? Discrete mathematics, right? In your home. High school. Who studied in the high school? From China for sure. Right? China, yes or not? No. When did you study it then? Adjacent matrix.
Last semester.
Last semester. Which course? Discrete mathematics. Which one? Calculus.
No. Linear algebra.
Linear algebra, right? Do you all study linear algebra?
No, it's
Right?
We studied it in the small semester.
Okay. Anyway, all right. So we have another two representations of graph. We have adjacent matrix and adjacent list. And actually, it's very, very simple. Okay? Adjacent, look here, adjacent matrix. What I have, two-dimensional array. Okay? I have two-dimensional array. Look at the graph. How many vertices we have in the graph? 4 vertices. Since I have 4 vertices, meaning that I will have 4 rows and 4 columns. And you will see why. Okay? Looking at this graph, do I have A connected to B? Yes. So we said the row and the columns both represent the vertices, right? I come. The first row, I assume it's representing which one?
A.
A. Second row represents which one? B. Third row C. Fourth row D. First column represents what?
A.
A. Second column represents what? B, C, and D. All right? Now, I have edge between A and B. The first one is what? The row. Second is what? Column. Your source, the current location you are at, is the row. The place you are going is the column. Now it's very easy. So I come to here. I have edge between A and B. Row A, column B. Row A, which one? This one. Okay? So row B, column B, which one? This one. So what I do, row A, column B, 1. So there's a connection between A and B, and just put 1. So it is unweighted. 1 mean connected, 0 mean not connected. Okay? Coming to here, I have A to C, right? A, C,